Hello and welcome to this video on multi-group confirmatory factor analysis and measurement equivalence testing. My name is Geiser. On this channel I present weekly statistics tutorials usually related to multivariate statistics including structural equation modeling, confirmatory factor analysis, multi-level analysis and latent class analysis. If this is something that interests you, then please subscribe to this channel. Also, don't forget to hit the like button and to check out the description for additional resources, including a link to my free weekly stats newsletter and additional videos and workshops. In this video here, I want to provide an introduction to multi-group confirmatory factor analysis and measurement equivalence testing, and I want to give you a sense for the different levels of measurement equivalence and what they mean when we conduct confirmatory factor analysis with multiple groups. So first of all, why would we use multi-group confirmatory factor analysis? Oftentimes, when we conduct research, we have an interest in comparing different groups, for example, males and females, or maybe people from different countries or different cultures. Maybe also we have an experimental design or quasi-experimental design where we compare a control group to multiple experimental or intervention groups to see if a treatment or experimental manipulation had an effect. And so what are reasons to do this with confirmatory factor analysis as opposed to t-test or analysis of variance? Confirmatory factor analysis is a much more flexible tool for group comparisons than analysis of variance or an independent samples t-test, because multi-group analysis and multi-group confirmatory factor analysis allows us not only to compare means across groups, but we can also compare variances, factor variances across groups. We can also compare correlations, covariances across groups, and path coefficients in extended structural equation models, so that we could do a moderator analysis with latent variables. If our grouping variable is, our moderator is a grouping variable, then we can look at whether path coefficients or regression coefficients are different across groups, indicating a moderator effect. And so there are a lot of things that you can test with confirmatory factor analysis that you cannot test with analysis of variance. You get an overall test of model fit. You can test assumptions such as measurement equivalence, as we will see here shortly. And also the procedure has less restrictive assumptions. For example, in analysis of variance, we have an assumption of homoscedasticity, meaning equal group variances in the population. And in multigroup CFA, this is not something that we need. Instead, we can actually study group differences in the latent factor variances as part of the analysis, and those might be interesting to look at. For example, when you have different cultures, you might be interested in finding out whether there are differences in the amount of individual differences on a given construct, regardless, so say, of measurement error. And that's another reason why we like to use multi-group CFA, or an additional advantage of using that method over ANOVA, that we can account for measurement error and we can look at latent variances, latent covariances, and latent means instead of looking at observed variables which contain measurement error. So there are many reasons why multi-group CFA offers a more flexible analysis for the comparison of multiple groups. And one aspect of multi-group CFA that I also see as an advantage is that it allows us to test the implicit assumption of measurement equivalence across groups, or we also say measurement invariance, and I'm using these terms interchangeably here in this video. What does this mean? Measurement equivalence, broadly speaking, means that we would like our measurements, our items, observed variables, indicators to have similar or the same, ideally, psychometric properties across the different groups. So we want our factors, our latent variables, to be comparable in terms of their units of measurement and in terms of the origin of measurement. And perhaps also we would like to see or test whether our measures have equal precision when they are used in different groups, meaning whether the measurement error content is comparable across different groups. And this is something that we in ANOVA and when we do t-tests or simple regression, this is a kind of something that we assume to hold across groups. So when we compare groups with a t-test or group means with ANOVA or regression, then we implicitly also make this assumption that the variables are comparable in terms of their metric, and that is not something that is necessarily always the case. For example, when you compare different cultures in terms of latent variables, then it could very well be that there are language differences when you translate a scale that lead to there being measurement non-equivalence across those cultures, meaning that the measurement instrument does not function in the same way. Maybe some items are perceived as more difficult in a given culture, or people have a harder time agreeing with certain statements for cultural reasons. And so this is something that we should study instead of simply assuming that measurement equivalence holds true. And so in this video here, I want to discuss the different levels of measurement equivalence that we can test through Multigroup CFA and give you an understanding for what they mean and which ones are required for which kinds of latent variable comparisons. Widerman and Rees in 1997 proposed 4 different levels of measurement equivalence that I will cover here. First is configural factorial invariance or configural measurement equivalence. Second is weak factorial invariance, also known as metric invariance. Third, we can look at strong factorial invariance, also known as scalar invariance. And then finally, there is strict factorial invariance also. I want to go over each of these levels of measurement equivalence based on an example. So here we have a very simple example, a one-factor model with 3 indicators that we want to compare across groups. You can, of course, do this with more than one factor. You can do this with more than one indicator, and you can do this with more than 2 groups. So this serves simply here to simplify my presentation. And then the generalization of this to more factors, indicators, or groups is straightforward. So assuming that we have 2 groups and this one factor model, what does a configural measurement equivalence model require or look like? So configural measurement equivalence means that we have the same number of factors in each group. So here we have 1 factor in each group, and we have the same configuration of factor loadings, meaning the same variables load onto the same factors in both groups. So we have, so say, the same pattern of factors and loadings, and that's given here. We have the same 3 indicators that load on the same factor in both groups. However, factor loadings, intercepts, and error variances are not restricted to be equal across groups. So we have a measurement equation with group-specific parameters, and that's expressed here with the subscript G. The subscript I is for the variable or item. So for example, I equals 1 would be the first variable right here and right here. And then the index G indicates the group. So here, for example, we have the first indicator in group 1. So that variable has the index or is labeled as y11. Whereas this variable is the same one in group 2, consequently labeled y12. And you can see that the additive constant or intercept in this equation alpha ig also has this group index, indicating that it could potentially vary across the groups. So there need not be invariance or equivalence of the intercepts across groups with configural invariance. Furthermore, also the factor loading or multiplicative parameter lambda ig has an index g for the group, indicating that also the factor loadings can be different. For example, lambda 21 need not be equal to lambda 22 under configural invariance. And likewise, the factors can be different, so they have a group index, and also the error variables can be different, have an index I and an index G. The next highest level of measurement equivalence is so-called weak or metric measurement equivalence. Weak measurement equivalence has a slightly different measurement equation where you can see the index G has been dropped now from the multiplicative parameter lambda I. So lambda I is the factor loading and it does no longer have an index G, indicating that it can no longer vary across groups. So here in this two-group example, you can see this from the fact that lambda 2 in group 1 is now the same as lambda 2 in group 2 for the variable y2. So this is no longer dependent on group, it's set equal across group, as we say. Likewise, lambda 3 can no longer differ across groups and is the same here. With metric invariance, we have the same units of measurement for the latent variables, and therefore we are now allowed, or we could say we can now make meaningful comparisons of the latent variable variances across groups. These are now comparable because tau 1 and tau 2 are now measured on the same scale in terms of the units of measurement. They still don't have the same origin of measurement, so the intercepts can still vary across groups, and therefore we can't compare latent variable means yet, because those mean differences could, if we see any, those could either be due to latent variable mean differences or intercept differences or a combination. And so with metric or weak invariance, it would not be wise yet to make comparisons of the latent variable means, but we can make comparisons of the variances, and we can make also comparisons of covariances. If we have multiple factors in each group, then we can compare those covariances under metric invariance. Next is strong or scalar measurement equivalence, and you can see that again the loadings are invariant across groups, but now also the additive constants no longer have a group index. So alpha I is the intercept, and alpha I can no longer vary across groups now as well. Now alpha I is not included here in the path diagram for simplicity, but it's also now equal across groups for each indicator. As a result, we can now not only compare variances and covariances across groups, but also the means or expected values, e tau 1 and e tau 2, are now comparable because the items have the same intercepts, the same origin of measurement, and as a result, any mean differences are now attributable only to latent mean differences because the intercepts are set equal and the loadings are set equal. And the error variables don't have means by definition, so epsilon does not contribute to the mean structure. Only the intercepts and the latent variables can contribute, and so if there are any differences now, then those would be attributable to true latent mean differences. So strong or scalar measurement equivalence is required or is desirable if you want to compare the latent means. And notice again that this is something that we implicitly assume when we conduct tests of mean differences using a t-test or an analysis of variance. We don't even test it. We just assume, yes, these variables have the same origin and units of measurement and they're comparable. And so here we have an opportunity to test that assumption before we make that comparison. Finally, there is strict measurement equivalence. Strict measurement equivalence implies the same restrictions with regard to the intercepts alpha and the loadings lambda. So those are still equal across groups. And now in addition to that, we also make the assumption that there's a common error variance for a given variable. So variance epsilon ig is equal to variance epsilon I. So we can drop the index g for all I and for all g. So for a given variable, the variance of epsilon, for example, epsilon 1, 1 would be the same as the variance of epsilon 1, 2. And so that implies equal precision of measurement, meaning the variables then have the same amount of error variance. And that might be something that might also be worth examining. For example, if you try to translate a scale, you want to establish an existing scale in a new country with a new language, you're translating a scale to Spanish or to Mandarin Chinese or something like that, and then you would want to know, are these scales equally precise in terms of the measurement? And so that would be then tested with the strict measurement equivalence model. Now, strict measurement equivalence is not required for latent variable comparisons. So the latent means you can compare even if you have just strong invariance, and latent variable variances and covariances can be compared even if you only have weak measurement equivalence. But strict measurement equivalence is neat to look at also because it allows us to test that assumption about the equal precision of measurement, and also because you would save additional parameters if you could assume strict measurement equivalence. Then you would not have to estimate all the individual error variances. I hope you found this video useful to learn more about multi-group confirmatory factor analysis and measurement equivalence testing across groups. Please check out my playlist on this channel as well on multi-group analysis, where I show how this is done in Mplus, and I discuss the different levels of measurement equivalence and how you can test them with Mplus in those videos on that multi-group analysis playlist. Also, if you like, please leave a comment in the comment section. Don't forget to subscribe to this channel and to hit the like button and to check out the description for additional resources, and I'll see you next time.